2-1, power and radical functions. So a power function is anything in this form. F of x equals a times x to the n power, where a and n are non-zero constant real numbers. It's also a monomial function. So I think of a monomial as one term of a polynomial. So we're not looking at that entire polynomial function. We're just looking at a little piece of it. So we're only looking at x being raised to a power, and then of course there's a coefficient. So we're going to look at a bunch of different graphs, and we're just going to analyze those. So this first one is when n is even. So that means I have an even exponent like x squared, x to the fourth, x to the sixth, and we have a positive leading coefficient. So we know, like with x squared especially, if it's a positive leading coefficient, we have some kind of a quadratic shape that goes up. If it's fourth or sixth power, it's still going to have that general shape. You'll see it'll be a lot steeper. So our domain, if we look at our x-axis, we have things negative x, positive x. So our domain is from negative infinity to positive infinity. Our range is not the entire length of the y-axis, though. Our range starts here at 0, 0 and goes up. So our range is going to be hard parenthesis there from 0 to infinity. Our x and y intercept are just 0. It is continuous, right? If I go to trace this, I can trace the entire function without lifting my pencil. So it's continuous on the entire domain on negative infinity, infinity. So when I say continuous on, I'm really referencing back to that domain. Symmetry, it is a symmetrical about the y-axis. I do have an absolute minimum at 0, 0. And now let's think about decreasing, increasing. So first, when I trace that function, I'm going down. And then after I hit 0 in the vertex, I change direction, and now I'm going up. So I have decreasing from negative infinity to 0. And then from 0 to infinity, I have increasing. My end behavior, we want to look on the left as x goes to negative infinity, and we want to look at the right as x goes to positive infinity. So let's see, as we go to the left, as I am looking at x going towards negative infinity, my end behavior is what are y's doing. And as I'm going to the left for x, my f of x, my y, is going up. So f of x is going to positive infinity. And as I go to the right, as I go towards positive infinity, what are my y's doing? My y's are going up. So f of x goes to positive infinity again. The way that your book is going to write this, we're not going to be using this notation so much this year, except it is in your textbook, but the calc teachers prefer we do it this way. Calc teachers like this in pre-calc. In pre-calc, they want to save the rest to teach you next year. But the way you're going to see it in your book is they're going to say the limit as x goes to negative infinity of f of x. So they're going to talk about a limit rather than where is the f of x going to. That's going to equal infinity. And the other one would be limit as x goes to infinity of f of x is infinity. So they're going to write it that way in your book. So this is in your book. So just know that, like, as you're checking your answers, but if you would like to write it this way, I would really prefer that you write it this way. So now we're going to look at same even exponent. So again, like x squared, x to the fourth, x to the sixth, but now I have a negative leading coefficient, so my graph's going down. So domain again is from negative infinity to infinity. Because my graph is upside down, this time my range is from negative infinity to 0. And 0 should be a hard parenthesis, x and y intercept is 0. It's continuous, right? It's continuous over my entire domain. Just like it was before, I can trace the entire graph without picking my pencil up. I still have y-axis symmetry. Now I have an absolute maximum at 0, 0. Let's see, decreasing and increasing now. So when I start on the left up to my my vertex there, I'm going up, and then from the vertex, I'm going down. So first I'm increasing, then I'm decreasing. So I am increasing from negative infinity to 0, and I am decreasing from 0 to infinity. Let's see, end behavior. So as I have, as x is going to negative infinity, so as I'm going to the left, what are my y's doing? My y's are going down, so negative infinity. And same thing as I go to the right, so as x goes to positive infinity, my f of x, my y's are going down. All right, so next graph. So now we're looking at odd exponents. So an odd exponent would be like x to the first, x to the third, x to the fifth. And because it's positive, my line is going up from left to right. So this time my domain is also, I can have anything along my x-axis, so negative infinity to infinity. My range this time is also from negative infinity to infinity. So when I'm squaring or raising something to the fourth power, I can only get positives out. But now if I put in a negative number, I get a negative number out. So stretching all the way across my y-axis, x and y-intercept are still 0. I'm still continuous. And this time you can see that my graph, if I rotate it around the origin, 180 degrees, it would match up. So I have origin symmetry around that point. And I have no extrema this time. I don't have any max or min. So decreasing or increasing, let's think about that. So as I trace my graph from left to right, right now it's going up. I hit my point of inflection, right? It's not a max or a min, it's a point of inflection. My graph is changing shape, but I'm still going up. So I don't have any decreasing at all. I have increasing. I just have a point of inflection in the middle. And then end behavior. On the left, as x is going to negative infinity, so as I go to the left, what are my y's doing? Y's are going down. So f of x goes to negative infinity. As I go to the right, as x goes to positive infinity, what are my y's doing? So as I go to the right, my y's are going up. So my y's are going to positive infinity. And now, of course, we're going to look at odd degrees, but negative. So odd power again, x the first, x cubed, x the fifth, any kind of odd power at all. And negative means my line is going down from left to right, just like a line would. So domain and range are still, just like the last one, from negative infinity to infinity. X and y intercepts are still 0. It's still continuous on the entire domain. So still continuous on negative infinity, infinity. I still have that point symmetry around my origin. I still have no extrema, no min, no max. Decreasing or increasing, let's check that out this time. So if I start on the left, first the graph is going down. I hit that point of inflection, my graph is changing shape, but it's still going down. So it's decreasing on the whole thing from negative infinity to infinity, and it's increasing not at all. So one interesting thing to note here is that my domain, my continuous, my decreasing, these are all x's, okay? That interval notation is all x's. The only time I'm looking at y's is my range. So be really, really careful. I'm talking about what is the y doing and where on x is that happening. So my y's are decreasing. Where on x are they decreasing? They're decreasing from negative infinity to infinity. And last one for my end behavior, as x is going to negative infinity, so towards the left, my y's are going up. So f of x going up would be towards positive infinity. And as I'm going towards the right, towards positive infinity for x, my y's are going down. So x goes to positive infinity, f of x is going down to negative infinity. So now we're going to go ahead and try graphing a couple functions. So first one, y equals 1/2 x to the 6th power. So I have a positive 1/2. This is an even power. So I know I'm going to have some kind of a parabola-like shape. So I'm going to go ahead and make this. And we know it's going to be at 0, 0. So we are just looking for a quick sketch. That's what we want here. So I may make a quick table. If x is 0, y is 0, how about when x is 1? 1 to the 6th power is 1. Half of that is 1/2. Negative 1 would give me the same answer. When I raise negative 1 to the 6th power, I'll get the same thing as a positive 1. Let's just try 2 and negative 2 for kicks. X to the 2 to the 6th power, 2, 4, 8, 16, 32. That'd be 64. So 2 to the 6th would give me 64. Half of that is 32. So now I go to graph. So here's 1, here's 2, 1, 2. So when my x is 1, my y is only 1/2. But that next point is like straight, like almost a vertical increase there, right? So I'm just going to make my graph something like that. And then again, we are trying to analyze functions. So I know this is going to match up exactly with what I had earlier. My domain is from negative infinity to infinity. My range is from 0 to infinity. My x and y intercept and y-intercept is 0, 0. My symmetry is going to be y-axis. So I'm pretty much just copying everything that I had earlier, right? If I had my notes handy, I could do that. What else did we have? We did extrema. So I have an absolute minimum at 0, 0. And then it starts out by decreasing. So I'm decreasing here, it's going down, and then I go up and it's increasing. I think I forgot to write continuous too. So let's say continuous on the entire domain. So continuous on negative infinity, infinity. Let's see, we started out with decreasing from negative infinity to 0, increasing from 0 to infinity. What else are we forgetting? Oh, end behavior. So end behavior, the y's are always going up. So as x is going to the left, y is going up, so positive infinity. And as x is going to the right, y is going up. That was really fast. So on the next one, we're going to look at negative exponents. So negative exponents is going to be a whole different thing, and we're going to add some stuff onto this. So the first thing I would do is I would make my negative exponent positive, because I don't like graphing negative exponents. So I would say f of x equals 2 over x to the 3rd power. And then I would use some of my other graphing things that I know. So I can't have 0 in my denominator. It's undefined when x equals 0. So that means I'm going to have an asymptote at x equals 0. And then I have a bigger degree of x on the bottom. Bigger degree on bottom. So I am going to have an asymptote that's y equal to 0. So I know that my x-intercept would come from my numerator equals 0. I can't make 2 equal to 0, so I don't have to worry about that. My y-intercept would come from putting that 0 in for x and solving. Can't do that. So really all I have here are those intercepts, or sorry, those asymptotes. So here's my axes, and here's my asymptotes. One at y equals 0, and one at x equals 0. So because this is really a reciprocal, I am expecting those kind of shapes of graphs like this. But I just need to make sure I know what quadrants they're in. So I'm going to just check a couple values. And to check a couple values, I am going to use like x equals 1, and I'm going to use x equals -1, and I'm going to solve for y. So if x is 1, I have 2 over 1 to the third power, which is 2 over 1, which is just 2. So when my x is 1, my y is 2. So if I've got a point over in that first quadrant, then I know how to make that part of my graph. Because you're always wondering, like, is it in quadrants 1 and 3? Is it in 2 and 4? What exactly is going on? For the second one, when my x is negative, now I'd have 2 over -1 cubed, which is 2 divided by -1, which is -2. So -1 for x and -2 for y. So this one's going to look like this. So I do need to go through and analyze this function. And I also want to think about how this is going to be the shape of the graph. Anytime my a is positive and my n is odd, when I have a negative exponent there. Okay? So really quickly, if I have f of x, that's supposed to be an x. If I have f of x equals a times x to the, I'm trying to use the same letters, -n. If I have a negative and n odd, then now it's going to be in, here's these guys, it's going to be in these two quadrants. So it would just change that. And then if I had a, let's see, positive and n positive. So remember when I put in, or sorry, n even. So if my n is even, then I'm raising everything to the second power or to the fourth power. When I put stuff in, I'm only going to get positive stuff out. So in that case, my graph would just be in quadrants 1 and 2, where everything's positive. And if I had a negative and n even, then I'd be getting that even power where I'm making stuff positive, but I'm multiplying it all by negatives. So in that case, I would have a graph that's down here and is down here. So just some stuff about these reciprocal graphs. Now we still need to be looking at our graph. We need to be thinking about the domain. So our domain is that we can't have that stuff in the middle, right? So we go from -infinity to 0, and we go from 0 to infinity. Same thing for our range, because we kind of break where that asymptote is. So range is from -infinity to 0 and from 0 to infinity. Let's see, my x and y intercept, there's none. None. I don't have any extrema. My symmetry is origin. So they're going to ask me about continuity. So I'm not continuous because I trace this part of my graph and then I have to pick up my pencil to trace the other half. And because there's an asymptote in between those, and along that asymptote, it's going to infinity and to -infinity. Along that asymptote in the middle of it, I have infinite discontinuity. So infinite discontinuity at x equals 0. Because we're always talking about x's. Let's see, what else do we have? We did extrema. There weren't any, no max or min. Oh, increasing and decreasing. So for the first part of my graph, let's just think about it. I'm starting here and I decrease. For the second part of my graph, I start here and I decrease. So we're always decreasing. So we're decreasing along our entire domain. From negative infinity to 0, we're decreasing from 0 to infinity. So we're always decreasing. Remember, all of these are x's. The only ones that are y's are my range. Everything else is x. My domain is my x's. When I'm talking about discontinuity, I'm giving an x value. When I'm talking about decreasing, those are my x values where that's happening, beginning, end, beginning, end. My end behavior would be the last thing. And it's kind of interesting for this one. So as we go to the left, so as x goes to negative infinity, my y's are getting closer and closer to that x-axis. So my y's are going to 0. And as my x is going to the right, my y's are also getting closer and closer to that, that 0 as well. So they're getting closer to that asymptote, y equals 0. So now some stuff about radical functions. Radical functions can be written in this form. So we have a root, we could have an exponent also. The big thing is making sure that you know that this is equal to this, so that the nth root of x to the p power is x to the p divided by n power, x raised to that p divided by n power. Those are equivalent. Remember, we can only take even roots of non-negatives. Otherwise, it's imaginary. We can take odd roots of everything. We can have odd roots of negatives, but not even roots. So that's just a quick thing to remember. These notes are super long today. We've just got so many different types of graphs. When you look at the power functions, radicals, we still have to solve radicals. We looked at the negative exponent graphs, so lots of stuff here. So my domain on this one, my x starts at 0 and goes to infinity. So that's my domain from 0 to infinity. My range is the same. I don't have anything in any other quadrants except quadrant 1, so my range is also from 0 to infinity. My x and y-intercept are still 0. I am continuous on my entire domain, right? So I don't have like a left-hand side of that graph, but while I am tracing it, I'm not picking up my pencil to trace that shape. So when I am tracing it, I don't have to pick it up at all. So it's continuous on 0 to infinity. My symmetry, there is none here, but I do have an absolute minimum at 0, 0. So now we have to look at increasing or decreasing. If I start here, I'm going up. So there's no decreasing, but there is increasing from 0 to infinity. And then end behavior. There's no left-hand side. So we are going to skip as x goes to negative infinity. We just don't write that part. So my end behavior would be as x goes to positive infinity. What are my y's doing? So as I go to the right, my y's are going up. So my y's are going to positive infinity. So this is when I have an even root. Next, we're going to look at an odd root and what happens. And then we're going to do some solving. So when I have an odd root, now I can have those negative answers. So my graph stretches across the page. So my domain is now from negative infinity to infinity. My range is from negative infinity to infinity. And my x and y-intercept are 0. And I am continuous on my entire domain. I'm continuous on negative infinity to infinity. So I'm giving my beginning and my end x values where I'm continuous. I now have origin symmetry. I'm symmetrical about the origin. I don't have any extrema though. I don't have any max or min. I have this point of inflection in the middle, right? But it's not a max or a min or anything. It's just changing shape. It's not changing direction. So decreasing, let's think about that. So my graph is going up, and then the graph changes shape, and then it's still going up. So I don't have any decreasing, but I have increasing from negative infinity to infinity, and my end behavior. So I need to think about as x goes to the left, or negative infinity, as x goes to the right, or positive infinity. So as I'm going to the left, my graph is really going down, not to be confused with the plus sign that showed my slope was going up. All right, so my graph is going down. So f of x goes to negative infinity. And then as I go to the right, my graph's going up, which is going to positive infinity. So y's are going up to positive infinity. So this one's going down. So one is like looking from left to right, and the other one's like looking as you go to the left, so you're like starting in the middle. And I think that's really kind of a strange thing. We just have so many ways to describe graphs. It's a lot to keep it all straight. So now we're going to look at solving radical equations. And I know I'm talking really fast. We've just had so much. I don't want to make a 30-minute video. So for solving radical equations, we're going to isolate our root and square both sides. So to isolate, I'm going to have to add 3 on both sides. So 2x plus 3 is going to equal the square root of 28x plus 29. So let's go ahead and square both sides. I'm going to write it in this way so you can really see it was that next step. So now I have a 4x squared plus, my middle term is these two multiplied, 2x times 3 is 6x, and then doubled is 12x, plus 3 squared is 9. When I square the other side, I just get a 28x plus 29. So really quick, remember, I don't know where to put this. Maybe we'll put it over here. Remember, if I have a square root of x and then I square it, it's just x. But if I have x squared first and then I square root it, I don't know if I squared a positive or negative thing to begin with, so I'm going to get an absolute value. So be really careful about that. So I only have 28x plus 29 here, no absolute value. So I need to get everything on one side. So I have to subtract 28x. So I have a 4x squared minus 16x. 9 minus 29 would be minus 20. I notice that all of them are divisible by 4, and that's just a constant, so I'm going to divide by 4, and I can just throw that away. So x squared minus 4x minus 5, and then I need to factor. So x minus 5 times x plus 1 equals 0. So I either have x minus 5 equals 0 or x plus 1 equals 0. This is exactly the way I expect your work to look. We're skipping a lot of steps compared to last year in Algebra 2, but I still need you to write these two equations separately and give answers. So a lot of times when I work with these square roots, I can have extraneous solutions. So extraneous solutions are when it works when you're solving, but not in the original problem. So we have to check for extraneous. So in my original problem, let's see, that was 2 times. First, I'm going to check x equals 5. I also have to check x equals negative 1. So let's see, this would be 2 times 5 equals square root of 28 times 5 plus 29. So 10 equals, let's see, 28 times 5 is, I don't even know, plus 29. Calculator, let me check it really quick. So this is going to be square root of 169. So 10 equals 13 minus 3. So 10 equals 10. So we're good to go on that one. The other one, checking x equals negative 1. And I know you guys always think the negative solutions don't work, but that's not always true. We really need to check it. So 2 times negative 1 equals square root of 28 times negative 1 plus 29 minus 3. So this is negative 2, and this is, let's see, negative 28 plus 29 is going to be the square root of 1. So 1 minus 3 is negative 2, so this one works also. They both work. So if you can really start to pay attention when solving, you might see some patterns and then not have to check for extraneous. So that's a really good thing for you to be thinking about as you work through these is, can you figure out when there's going to be extraneous solutions? Can you predict that? That's really that higher order thinking that we're looking for in pre-calc. And I'm not going to tell you when. I need you to figure that part out yourself. So on this one, I want to isolate my root again. I'm going to start by subtracting 8. So 4 equals the cube root of the quantity x minus 2 squared. To get rid of a cube root, I'm going to cube both sides. And that looks kind of like a mess over on the right. So 4 cubed is 64. And on the right, I have the quantity x minus 2 squared. So now I'm going to square root both sides. And so now this is what I was talking about. Now I have the square first and then the root. That's an absolute value. And the square root of 64 is 8. When I have an absolute value, I need to write a positive and negative equation. So there's going to be one equal to 8, and there'll be one that's equal to negative 8. And I'm leaving the x on the right. I'm not going to just magically flip it over to the other side. We should be really fluent at solving equations. It doesn't matter which side x is on. And so I get 10 or negative 6. So let's go ahead and do a quick answer check again. So let's see, 12 equals a cube root of 10 minus 2 squared. Does that really work? Plus 8. So let's see, 10 minus 2 is 8. 8 squared is 64. Cube root of 64 is 4. So 10 works. And now let's check negative 6. So negative 6 minus 2, quantity squared, that's going to be a negative 8. But when I square it, it's going to be a positive 64 again. So I'm going to stop my answer check right here. I know that this one's going to work as well. So we have 2 answers again. And again, I want you to be really thinking about, how can I tell? Can I tell without showing all that work? Last problem. We have worked our butts off to get here, but we have one last problem. So this one, we have square roots on both sides. We cannot isolate either one of them. We have that one right there that's in the way. So our strategy is going to be square, then isolate our root, and then we're going to square again. So it'll be a miracle if we don't have extraneous solutions after all that, right? So when I square on the left, it's pretty easy. When I square on the right, it's going to be a little more complicated. So when I square on the left, I'll just have an x plus 1. But on the right, I've got a binomial to multiply out. So 1 squared would be 1. And then my middle terms, I multiply and double. So 1 times that square root, but then double will be 2 times the square root. And then plus my last term will be the square root squared. So just 2x minus 12. And then I want to kind of simplify the right side before I go adding and subtracting and isolating. So let's see, 1 and a negative 12 would be 2x minus 11 plus 2 times that square root. I have a feeling I'm going to be leaving the 2 in front of the square root because I don't think I'm going to be wanting to divide in the end, but we'll see. So now I'm going to subtract 2x on both sides. So I have a negative x. I'm going to add 11, so I have a plus 12. And I still have that 2 times the square root. So we're going to go ahead and square both sides. When I square on the left, my negative x squared would just be an x squared. Middle terms, I'd multiply negative x and 12, so negative 12x, and then double it. So negative 24x. Square the 12, 144. And then on the right, 2 squared is 4. And when I square the square root, I just have a 2x minus 12. So I'm going to clean up the right side and distribute. 8x minus 48. And then I'm going to have to get all my terms on the same side. Did a lot of work on this one. We're not even there yet, huh? And then once we get our answers, we still have to check. So subtract 8x on both sides. I'll have x squared minus 32x. And then I would add 48 on both sides, so I'll have a plus 192. And fortunately, I already checked the factoring on this. It'll be x minus 24 times x minus 8. And so now I can do my zero product property. So either x is 24 or x minus 8 equals 0, x equals 8. So now to check. And again, it's really great if you can figure out a system so that you're not always checking. So when I check, I'm checking 24 first. So that would be the square root of 24 plus 1. I'm having to go back on a piece of paper where I wrote it down and check. And then it would be 1 plus, because we've got to go back to the very original problem. 2 times 24 minus 12. So this would be the square root of 25. See, 2 times 24 is 48 minus 12, square root of 36. So 5 equals 1 plus 6. So that's not working. So this one's going to be extraneous. And let's hope the other one works now, right? So let's check x equals 8. So that would be, I moved it up a little bit too much, square root of 8 plus 1 equals 1 plus square root of 2 times 8 minus 12. So let's check this one. And again, we have to go back to the very first step. This is the square root of 9. 1 plus square root of 16 minus 12. 3 equals 1 plus square root of 4. Oh, good, this one works. 3 equals 1 plus 2. Yay, so we have one answer. So x is equal to 8. This was a lot of information very fast. I hope that you felt free to pause this as I went through these notes so that you could really get everything down. And my completed notes are also posted on Canvas, so you can just look at those as well if there's something small that you missed.